Chemical bonds are the result of atomic orbitals overlapping with each other. Whether it's two s orbitals coming together, two p orbitals coming together, or an s and a p orbital coming together, the thing they all have in common is they are sharing space with their outermost electrons to form a covalent bond. In this diagram, we can begin to see why a bond has a particular bond length. For example, two atoms here, separated some distance, have no attractive force unless they begin to move closer together. As they move closer together, then they start to overlap their atomic orbitals, and so the electrons become trapped in this region between the two nuclei. Because the electrons are feeling the interaction of two nuclei, then the atom is able to release some energy, creating an energy well. The bottom of this well corresponds to the bond length and represents the most stable point for the electrons in that bond. Moving further away requires an energy input, and if things start becoming too close together, then the repulsive forces of the two nuclei become an issue. So there's an optimum bond length for every chemical bond. Now, when we talk about bonds, we talk about valence bond theory. In valence bond theory, we're really talking about hybridization. How do the atomic orbitals change when they form a covalent bond? There are two ways in which bonds can form, or two types of bonds that we can have. The first type is known as a sigma bond. Sigma bonds are the direct overlap of either two s orbitals or two p orbitals or an s and p orbital. What they all have in common, though, is that the region in which they overlap falls directly between the two nuclei, and so it has the best overlap, it has the best interaction, it is the stronger of the two type of bonds. Pi bonds, on the other hand, aren't allowed to form directly between the two elements because the sigma bond is right here. So they have to move around much like a hug when hugging somebody else. You come in from the sides rather than taking a direct approach like somebody might when greeting you with a handshake. So if you want to think about a sigma bond as a handshake, a pi bond would be a hug. It comes in around. Because pi bonds come around and they're not directly between the two nuclei, they are a little bit weaker. But here's the thing you have to remember. The first bond formed is always a sigma bond. Each additional bond formed after the first between two elements is a pi bond. Sigmas are always the first bond formed. Pi bonds are only formed as you need increasingly more bonds between the same two elements. We can begin to see the effects of sigma and pi bonding here in formaldehyde. You can see between the carbon and hydrogen there's an overlap of an s and a p orbital here between this carbon and hydrogen, as well as over here between this carbon and hydrogen. Between carbon and oxygen we have a sigma bond, but we also have a pi bond here because in the Lewis structure we would need a double bond between the two. The first bond in all three of these is a sigma bond, but only the carbon-oxygen also has a pi. And you can see that that bond lies above and below where the sigma bond is. Here in acetylene, we can see that we have a carbon bonded to a hydrogen and another carbon. And what we see here is that the carbon and hydrogens both form a sigma bond, but the carbon-carbon bond here is a triple bond. There's a sigma bond, which you can just see right here as the purple, and then there are two sets of pi bonds creating a triple bond. So multiple bonds after the first must extend outside the direct region of space between the two atoms. Now a double bond is stronger than a single bond, just like a triple bond is stronger than a double bond. But the first bond is always the strongest, the sigma, and then the pi bonds are a little bit weaker, so there's not a doubling in terms of bond strength or bond energy just because you add another bond. It doesn't scale up proportionally. Now when we have structures that have resonance, what happens is the double bond is simultaneously placed on all three locations in this particular example with the nitrate ion. So because we have resonance, we have essentially one continuous bond going above and one below the sigma bonds here. So there's this highway for the electrons to travel around, and this really helps go a long way to stabilize the resonance structure and deal with that extra electron that would not normally be able to be maintained from just having a single bond there. So resonance must require a double bond, and a double bond that can be placed between multiple atoms without changing the structure. But because it's delocalized, electrons are free to move around, as opposed to being a localized situation where the electrons are trapped directly between two atoms. A sigma bond we describe as having localized electrons, but a double bond may or may not be localized. If you have resonance, and only if you have resonance, can an electron be described as being delocalized. Here's another example of benzene, which has 6 carbon-carbon bonds and 6 hydrogen bonds. And when we take a look at the double bonds here, they alternate, creating this delocalized racetrack for the electrons to roam around in. So benzene is an incredibly stable molecule, and it's one organic chemists love to talk about, because it has this resonance structure and this racetrack for the electrons to move around, providing a great deal of stability.